Do is get started today. We're going to talk about the last set of learning algorithms that we'll cover in this class, and that's going to be reinforcement learning. And so I want to start this lecture out not by telling you what reinforcement learning is, but by taking a bit of a detour to tell you about a completely different kind of mechanism that one could use in order to do learning. And so far in this class, we've sort of started with the following data set. And then given the data set, we've asked, can we build a model, some m of theta, with parameters theta that enable us to write down a loss function. So this loss function is going to tell us how good our model is at prediction relative to the actual ground truth labels that we have for the data set. And given this data set, we're then going to do minimization via gradient descent or via the direct method or SGD. And so in this lecture, what we're going to do is that we're going to find solutions using a completely different kind of method. And before we tell you why that's relevant for RL, it's worth asking you about whether you've seen this before. And so let's say that we were able to write down a recursion in via a function over real numbers. So x of n plus 1 is equal to cosine of x of n. So that's a simple recursive relationship. And so our goal here is to solve for x. How do we find some value of x such that x equals f of x? Who has ideas on how to try to tackle this problem? So imagine you got this as a question and someone was asking you, I'm going to give you a recurrence. You're going to tell me how to find a point x where x equals f of x. Ideas on how to even approach this? Yeah. Okay, so one potential solution is if you were able to find a closed form, so the solution, you might be able to write down what that x star looks like. But if I would actually just tell you in this case, I'm giving you the functional x and telling you what the recurrence is, and I wanted you to give me a number. I don't want the closed form, I just want the answer. How might you tackle that, even using numerical methods? All right, you have to come up with at least an attempt at this solution. So just give it a shot. It could be wrong, but that's okay. Okay, so calculate cosine over what? Okay, so let's say we started at, x0 is equal to 12. What is your suggestion? Okay, so you do cosine of x0, and you're going to say, put that into x1. What's the next step? So cosine x1, and you put that in x2. Right. And eventually, at some point, you might hope that you converge to some x star. And the point that you're trying to get at is maybe you converge to a point where x star equals cosine of x star, which is to say the method that was suggested here was to iteratively apply the function over and over again until you get to a point where the application of that function makes no change to that point. Remember, functions are things that change the input in specific ways. And if you keep applying the function over and over again, you end up in some cases, converging. And so there's a name for that algorithm, and that name is fixed point iteration. So how many of you have seen the algorithm corresponding to fixed point iteration in any context before? Okay, so let's talk about what this is and why it's useful. So given any xn equals f of xn, which is a recursion over xn, the fixed point iteration algorithm says you will start at some point x equals x naught, which is your initial point. And then what you're going to do is do x equals f of x. So all you're going to do is keep applying x to f of x and repeat that process again and again until you meet a stopping condition where the absolute value of x minus f of x is less than some predetermined threshold. So that's it. It's a really simple algorithm. So my next question to you, since you're able to figure out what the algorithm is when is this algorithm going to give you a good solution? Again, I'm not necessarily looking for a mathematical definition. I'm trying to get you to think about the intuition for the function when it might work. Yeah?
We know that like through enough repetitions we will reach some sort of approximation that is desirable.
Right. So you want it to reach some solution that's desirable. But do you think this would work for all functions? So let me give you an example. Do you think this would work for f of x equals e of x? Just run this algorithm in your head for f of x equals to e of x and tell me if it'll work. Why? Yeah. Right. So there's some notion of a blow up that'll happen because you keep applying the exponent function to some input x, and it gets larger and larger and blows up exponentially. So that's exactly right. When might this work? Yeah. Right. So Lipschitz continuity. So do you want to attempt like a hand-wavy definition of what Lipschitzness actually is? Okay, so I'll repeat that just a bit louder. So if you have 2 points, the answer was Lipschitz continuity is a condition that a function satisfies. It says that if you have 2 points, x1 and x2, and you can bound their difference, so you can bound the vector norm between 2 points in any vector dimensional space. So that's norm x1 minus x2. Lipschitz continuity says that your function also satisfies a bound on the application of the function between those 2 points. So the right-hand side is the distance between the 2 points, any 2 points in a high-dimensional space. And the left-hand side is the application of those function to any 2 points in those high-dimensional space. And if your function satisfies this property, it's said to be Lipschitz continuous, where this is the Lipschitz coefficient. Now, there's a simpler condition. So Lipschitz continuity is sufficient to prove this condition, and that's essentially that f is a contractive map. So if you have not heard this word before, it has a very intuitive understanding or meaning. It's basically saying f is some function that squishes inputs. So e of x is a function that does not squish inputs, it blows it up. So the opposite of that is a function that is going to contract the space of inputs that it is applied to. And when f satisfies the property that it is a contractive map, which in this case the cosine does, then you can guarantee that this algorithm will converge to the unique fixed point. And there's a mathematical theorem that talks about uniqueness, which is Banach's fixed point theorem. And so that's just a bit of mathematical background to get you started to think about the algorithms that we're going to use. And I want to talk about why this is fundamentally different from the algorithms you've seen before. In the past, we've come up with a model and we've come up with a mechanism in order for us to be able to take that model and train it on some training data using gradient-based method. Here, when we talk about RL, we're going to think about how to come up with the optimal policy function. And to come up with the optimal policy function, we'll show that you can recover the policy by running fixed point iteration on some object. So that's basically a preview of what we're going to talk about in the context of value iteration. And so now we have some of the mathematical background that we need to start thinking about RL. And in supervised learning, so far, we've talked about, actually just before we go, any questions about the math behind contractive maps or fixed point iteration? Are folks comfortable with at least the intuition for that idea? So as long as you can prove that this function has the property that it takes inputs and then it squishes them, so the application of that function, the range of that function is in some sense smaller than the domain, then that function is a contractive map. Any questions, thoughts, concerns about that idea? Okay. So with that, if at least people are comfortable with the intuition behind that idea, let's jump into RL. So in supervised learning in the first half, we talked about how we can use models to predict labels of undesired behavior. In unsupervised learning, we had no labels, but we believed that there was latent structure that we might want to uncover. And now we're talking about reinforcement learning. And reinforcement learning is really the algorithms that are responsible for training agents to operate in an environment to achieve a certain notion of a reward. What does that mean? So think about this movie where you have an agent that is going to observe the world and take interactions with the world. And eventually, in the long term, it has some idea of a reward that it wants to achieve. So our goal in reinforcement learning is to come up with the design of a policy that tells us how this agent should act. And so this world of reinforcement learning is done within the context of this mathematical framework called Markov decision processes. So remember, the math is useful and interesting to formalize things that are relevant, but really our goal is to come up with good ways for an agent to behave. So we have some environment that we do not get to control. So the environment is given to us. So a good rule of thumb in the context of this lecture is to ground yourself in the context of your favorite video game or think about automating a task that requires you to interact with some kind of an environment. Whether, let's say you were designing a robot to solve a maze, or you were playing your favorite video game. Take, for example, Super Mario. It's good to instantiate yourself in an example because it gives you a concrete way to think about what each of these mathematical terms might mean. So in the context of Super Mario, the environment is just this emulator that tells you what happens when your character moves forward, what is the new image that you see on your screen. So the environment is a thing that takes as input actions, AT, and then it spits out states and rewards. So the action might be move Mario to the right or make Mario jump, and if the jump happened to be under one of those coins, then the new state is a version of the environment where that coin is no longer present because it's been consumed, and maybe the reward is the total number of score that Mario has plus 1, because now you've gotten that additional coin by virtue of jumping on it. So any questions about what the environment are in the context of at least a simple example of Mario? Just by show of hands, has anyone not played Mario? I'm just going to assume that it's sufficiently culturally relevant that I can use it as an example. But if not, just let me know. OK. So that's what the environment does. It takes actions, and then it spits out the next state and a potential reward. And what the agent is going to do is that the agent has a policy distribution. So the agent is going to look at the state that it's in relative to the environment, and it's going to come up and compute a distribution over actions. So remember, whenever you see this notation, sample from a distribution over action, you should think of the case where you're controlling a character in Mario, where the action might be go up, crouch, go right, left, A, or B. Those are the possible actions that you can take in the context of the game. Let's just pretend you're playing this on a Game Boy emulator, and now you have these 6 actions that you can take. So your policy function is going to take as input your state and print out a distribution over the possible actions that this agent could do. So you're going to get 0.1, 0.1, 0.1, 0.1, maybe 0.4, and so on and so forth. And this is the distribution that you will sample from in order to pick an action. So this operation of sampling means you get the parameters of some distribution, and you sample, in this case from a categorical distribution, to get a single choice of action. Now, st plus 1 is said to be sampled from this P of st given and at. What is that? So this is what we call the dynamics function. The dynamics function is a function that takes the previous state and action and tells you what the next state is. It is basically a function that characterizes how the environment might behave, either deterministically or stochastically. So let's consider the example of Mario, which is, for all intents and purposes, a is a stochastic environment, because when, let's say, Mario jumped, you got the coin, and then in the next state, the environment has to decide what is the probability of one of those new mushrooms occurring in the screen. There's some probability associated with that. It doesn't always appear. And so it's a probabilistic environment because of there's a non-zero probability of, say, a mushroom appearing walking towards the character on the right. So you're going to have this function that characterizes the probability distribution over all possible states that could exist, and you're going to sample one and actually observe that next state. So that's what the transition dynamics do. And finally, you have a reward function, which may or may not be stochastic. In the example that I gave you, where you jump up underneath a coin and you are guaranteed to get that coin, it's a deterministic reward. But there might be scenarios where you have stochastic rewards as well. And so this entire loop put together represents a Markov decision process. It represents a sequential decision-making process where you have an agent at a single point in time, observes the current state of the world, and decides how to interact in the form of an action distribution. An action is sampled, it interacts with the environment, and the environment gives out a reward, or it gives out the next state. Yeah?
Why do we look at the next state as like sampling from the probability distribution? Because once the action is set, that action will lead to one possible outcome. So why don't we just split the...
Well, in the example of Mario, for example, like let's say you are underneath that coin and then you jumped up. You will get that coin. So in the next state, you know that that coin will no longer exist. That part is deterministic. But the part that is not deterministic is whether or not a new mushroom comes walking in from the right-hand side of the screen. So the occurrence in that case of the mushroom is stochastically determined, which is why we sample from a probability distribution over possible future states. Any other questions about the formalisms here? Or just any of these words and ideas? So if most of you are comfortable with that, then we can think just a bit more about some of the words that I mentioned to you, which is how to describe the dynamics of the environment. And so I gave you the example of Mario, where the state of the environment might be the RGB image corresponding to the picture that the agent actually observes. But this idea of a state is very general, because you might not be playing Mario, you might instead be thinking about playing air hockey. In which case, you can ask, what is the state of a puck sliding on a frictionless table? So you can think of the state as a description of the environment in sufficient detail to determine its evolution. So if you wanted to build an agent to automatically play air hockey, what would the state variables be for this puck on this hockey table? Yeah.
X and Y as well as velocity.
Yep, X, Y, and velocity would give you sufficient amount of information to characterize the evolution of motion of this puck on this table. And so that would be a three-dimensional vector that characterizes the state of this particular game. And so the next assumption we make in modeling the dynamics is what's called the Markov assumption. So Markov assumption is very simple. It says that the state at time t plus 1 depends only on the state and action at time t and not on the previous states and actions that could have been taken, which is to say that the state represents a sufficient summary of the information content that an agent would need to use in order to decide how to act. So let's imagine that you're playing Mario. It doesn't matter if you jump down a tunnel 20 frames before. The only thing you need to know in order how to act optimally right now is the current set of states and actions that perhaps you took in the previous stage. That's what the Markov assumption says. And as you go on to more and more advanced machine learning classes, you're going to have a lot more instances of where this Markov assumption show up, because it's a pretty foundational assumption that appears in many temporal modeling problems. Next, to describe the dynamics, you need to specify, as I mentioned, the transition probabilities. So we've only talked about this idea, this P of st plus 1 given st at in the abstract. But in reality, it's really tricky to represent these probabilities, because if you think about even the simple example of a ice hockey puck this air hockey table, you have to represent all possible x, y velocity coordinates that could exist and are valid on this ice hockey puck, because that is the distribution that you need to be able to correctly characterize. And as you can imagine, even for very simple examples, it's often very challenging to specify what these transition probabilities look like, because they require you to know something about the physics of the world. And that might be easy when you're working with Newtonian physics, because you can exactly say what is the probability distribution over the next xy coordinates and the current and the velocity, given that the puck is at position xy moving with velocity v, and the action might be push the puck with a certain amount of force. Like, given that information, you can exactly compute what the probability distributions are in the next state. But there are many examples where this is intractable. And so knowing the transition dynamics of many practical systems can be very challenging. And so in this lecture, we'll also assume that the state is fully observable, which is just a fancy way of saying that there's nothing else that is acting on the agent that might deviate, that might result in aberrant behavior, which is to say the agent gets to observe all the relevant details about the information in the system that it needs to make a decision on what the optimal action is. So that's the states and actions. And so, let's say you're controlling a robot hand, you can think about what the set of states and actions could be. So the states might be the positions and locations of all of the sensors in this robotic arm. And the action might be whether one of these sensors is moved and in which direction and with how much force. The other set of states could also be the orientation of all of the colors in this Rubik's Cube. And you can imagine that the combination of sensors for the robotic arm as well as the orientation of the Rubik's Cube might present enough information for the overall system to make an adjudication on what to do next in order to solve this Rubik's Cube using the robotic sensors. So you should think of, when you're asked, what is the state variables, think of what kind of information do I need in order for an agent to act independently so that they might reach some desired goal. Okay, and finally we talk, before we talk about rewards, we're going to talk about policies. And so policies, as I mentioned, are the mechanisms that agents use in order to act in the world. And so the policy could be deterministic, which just says that for some function of states, you know exactly what the action should be. Or it could be stochastic, where you are sampling an action. And this might represent uncertainty on the behalf of the agent, where if the agent is uncertain about whether to open door A or door B, it might represent that uncertainty via a probability distribution over which action to take. And with stochastic policies, the distribution over rollouts or trajectories factorizes. So what does this mean? Whenever you see this word rollout or trajectory, it's referring to a tuple of state action pairs that have been evaluated over multiple different time steps. So let's say you are playing the game of Super Mario and you tracked what the states and the actions were for t time steps, so t frames of your video game. In that case, when you have a stochastic policy, you can ask, what is the joint distribution of observing the states and actions that you actually saw? That joint distribution factorizes according to this distribution. So this says that you start with some state with probability S1. Given probability S1, your agent takes action A1 with probability pi of A1 given S1. And then you move to a new state, S2, given the state S1 and action A1 that your agent took. And then you repeat this process t times. So this is nothing more than, just like we talked about Bayesian networks and naive Bayes, this is converting that loop that I showed you in the context of MDPs into factorized probability distributions. And so the fact that policies need only consider the current state is a consequence of the Markov assumption. So you'll see here that this policy, for example, pi of A2 given S2, need only consider and condition on S2. It does not need pi of A2 given S2 comma S1, because we've made the Markov assumption here and the state variable S2 is independent of S1. Okay, I apologize. I meant to say that the policy distribution of A2 is independent of S1 as long as you condition on S2. So why does this matter? At the end of the day, what you actually want is to have an agent receive a reward from some distribution over rewards. And so, at least in this lecture, we'll assume that all rewards are deterministic. So you have a function that looks at the state and the action and then prints out a reward. So the last piece of notation that you need to know is called this idea of a return. So the return is just a number g. And g is the sum of rewards that you get from t is equal to 0 all the way to some capital T or infinity. And you can have two types of returns. So you can have returns that are undiscounted, or you can have returns that are discounted, where gamma is the discount factor. Yeah.
Can you do a combination, or do you have to choose?
Usually, you have to choose one or the other. And people, almost all of the theory and practice works with discounted rewards. And so gamma is this hyperparameter called the discount factor, which determines how much we care about rewards now versus rewards later. So let's think about what happens when gamma is very close. Let's say gamma is 0.1. When gamma is 0.1, you pay a lot of attention to the reward that you get right now, and you pay a little less attention to the reward that you get in the next time step, and even less for what happens into the future. So you can think of gamma as basically changing the amount of influence that actions that you take in the short term have on how the agent will behave. So it trades off between long-term rewards versus short-term rewards. Yep.
Is there like a version of reward that instead of like valuing short-term gains, values long-term gains?
Yeah, so you can come up with ways to modify this so that you have, let's say, a number here that is perhaps small and that gets larger. But the problem that you often run into when you're trying to make that trade-off is that unless you know exactly how many time horizons you want to solve the problem in, it becomes really difficult to come up with a nice mathematical function on how to do that. Because if this series can go to infinity, it's much harder to design functions that satisfy that property. And so the choice of how you design a reward function often has a huge role to play in the quality of results that you get. And so you can look at this YouTube video of, I think it's a video of an agent that's been trained to play Pong that shows you the influence of changing the reward choices when you come up with this agent. But moreover, you can think about simple examples of a game like chess or Go. One option might be to give the agent a +1 for a win, a 0 for a tie, or a -1 for a loss. That might be one choice of reward signal that you end up using to build this agent. Another one might be the total amount of agent's territory, the total amount of territory, which in the context of chess might be the opponent's pieces, that you capture. So you might want to encourage your agent to capture more and more of the agent's territory in the context of pieces. And both of these are valid rewards in the sense that they encourage the agent to learn to win the game of chess. But both these rewards can have very different influences on how the agent actually performs in real life. So you can imagine a strategy in chess that encourages the agent to, for example, sacrifice really influential pieces early on in return for a quick checkmate. That is a strategy that is much more likely to be learned by option 1 than it is by option 2. Because in option 2, giving up a piece would be penalized because of the choice of the reward function. And so the choice of how you design this reward function can play a really important role in the qualitative characteristics of how your agent achieves the goal. And in general, the design of reward functions is like a really important area of research. So if you remember from the ethics module, we talked about this idea of aligning large language models with RLHF. And you can think of all of these issues of playing out even within that context, which is how do you design a good reward function? In the context of LLMs, you have humans saying this is good and this is bad. So then you can ask, who are those humans? and do their values align with what you would like your LLM to adhere to when you're using it for a specific task. And so the design of rewards is inherently in a subjective exercise, but you should know that those choices matter in terms of the quality of results that you get when you evaluate your agent as well. And so it's been a bit dry for the last 10 minutes as we've been going through a bunch of notation, but the reality is this is what you need to know for a Markov decision process. It's basically this tuple of 5 things: the states, the space of all possible locations that an agent could be in, the action space, which is the space of all possible actions that an agent could take, the transition probabilities, which tells you what states you move into as a function of the state you were in and the action that you took, the reward distribution, which tells you how much incentive you have given the current state and action that, given the state that you're in and the action that you took, and the discount factor, which tells you how much to weigh long versus short-term gain. So these pieces put together characterize this MDP, and they define the environment that the agent operates in and the objectives it's supposed to achieve. So thus far, we haven't talked about planning or learning or any such thing yet. We've just set the stage for what reinforcement learning does. So in the future, if you do take a class in reinforcement learning, almost all of the research or almost all of the academic material that you learn makes use of the Markov decision process formalism. So at least you should know what that formalism is. Okay, any questions so far about MDPs? So that was mostly just notation, and now we're going to move on to thinking about finding a policy. And so there's 2 scenarios you need to be aware of. The first case is called planning, and this is the case where you have a fully specified MDP. And what that means is that you have access to all of the 5 things that I mentioned in the previous slide. And the crucial part of that is the transition probabilities, which is to say you know exactly the distribution of future states that could occur given the past states that you have. The second scenario is called learning, and this is the much more practical scenario that a lot of research operates in, because in learning, what you have is an agent that is going to interact with an environment with potentially unknown dynamics. So if you want to have an agent operate in the real world, it is way too strong of an assumption to assume that you can characterize exactly the transition dynamics, because the world has way too much stochastic variation in it for you to write down those probabilities. And so you want a mechanism to still train these agents to operate correctly, and that's where the class of methods called learning comes in. So we'll go through one example in this lecture today of both planning as well as learning. And so in chess, it's much more likely to be a case of planning, because even though it's more complex, you can still argue that on an 8x8 board, you can come up with distributions over what the next move could be, because you have constraints on what valid moves are, and you might have historical data to come up with empirical estimates of those probabilities. But in something like Super Mario, you're much less likely to think that you have a full stochastic distribution over all possible future states. And you're much more likely to work in the mode of learning, where you let an agent just interact with an environment to figure out what it should do next. Okay, so questions about the distinction between planning and learning. Really, the main difference is about the fact that you have a fully specified Markov decision process in the context of the dynamics function. And so that brings us to the first algorithm that we're going to talk about. So thus far, we've set up what RL is. We've talked about the formalism for RL in the context of Markov decision processes. And now let's talk about value functions. Value functions are the loss functions for RL. They're kind of like one of the mechanisms we use in order to understand what is good and what is bad. In supervised learning, we use mean squared error, or we use softmax cross entropy. In reinforcement learning, we're going to use this value function. So what is the value function? The value function is a function that takes as input any given state that the agent could be in, and it tells you what the expected return is conditional on being in that state and on moving forward under policy pi. So it is a function, and it's going to depend both on the state that you're in and the policy that your agent follows into the future. So let's write this out. So you have an expectation over pi. So pi, remember, is the agent's policy distribution. It tells you how the agent might behave stochastically in the future. And you have the return that the agent is going to receive. And this is the discounted return from k is equal to 0 to infinity. So this is the infinite horizon value function. And so this is essentially saying how much return can I expect going from now into the future, assuming that at time step t, I am in state S as an agent. And you should think of this as measuring the inherent desirability of any state. Because in this world that you're in, there is a goal that you intend to get to. And each state that you're in is a pathway to get to that goal. So what we're going to do in order to train intelligent agents to be able to achieve certain goals is that we're going to characterize the value of being in any given state. Because that is the thing that would enable us to encourage agents to move from states that have low value to states that have higher value, eventually moving towards a state that represents the goal state. So if you're trying to solve a maze, the value of being in the goal state should be the highest among all of the value of every other state. The value of being in a dead end should be very, very low. So any questions about the equation corresponding to the value function here? Yeah.
Very quickly, earlier we said that the reward is based on both the state and the action.
Yep.
But now we're taking the value of the reward with just respect to the state. So how are we just like setting the action as constant, or are we just?
No, we're following actions that are sampled according to policy pi. So what we're saying is that we're currently in state S. We're going to look at pi and sample some action. That's going to give us some reward. And we're going to add to it, this discount factor if necessary, and then we're going to sum it all up. And then we're going to repeat this process again. That's going to move us to a new state. And all of that is sort of compressed in this RT plus K. So we'll see what that looks like when we unroll it. And so this is an example, as I mentioned before. If you were trying to solve a maze, you might set this problem up where you get a reward of -1 per time step to encourage the agent to solve the maze as quickly as possible. So this is your environment. Each of these is a valid state that your agent could be in. Your goal is to get the agent from the start state to the goal state. And we'll assume that we have a deterministic policy here. So the agent is going to do exactly one thing at any given state. And so this might be one choice of policy that could be characterized in pi, in the function pi. What is this policy saying? Well, if you were in this state, this policy is saying move to the right. So agents that are in this state are going to move here. If you're in this state, it's saying move up. So when you apply pi to your current state, you will get a new action AT. And that action is given to you by these arrows. So that's what this diagram is telling you. And now if you interact with the environment based on the current action, it will move the agent along this maze. So from here to here, you apply the action to the environment and your agent moves. And you do this again, your agent moves here. And you do this again, your agent moves here, here, and so on. And you'll see here that this is a good policy. And the reason why this is a good policy is because if you follow the arrows, you will actually solve this maze. And that's true regardless of where you start from. And so you can ask for this choice of policy, for the choice of policy that I showed you in the previous slide, what is the value function? And you can write down the equations that correspond to the value function by computing the equations that I mentioned before. And the easiest way to see that is to think about what happens right before the goal state. So right before the goal state, you have a value of -1. Why? Because you get you have to pay the reward is set up so that every step that you take has a cost of -1. So this is the value of being right next to the goal state, because that's just the cost that you have to pay to move one step to the goal, given this policy that tells you to move to the right. Let's go one step back. At this state in this maze, the value of this state is -2. It's indicating to you that you need to pay a cost of at least 2 steps to eventually reach the goal under policy pi. And you'll see here that if you backtrack, you can eventually write down what the value function is for this entire system. Yeah?
Like in reality, would we need to give a policy to the squares that would never be reached by following the policy from the start? Because like if this is a real maze and we follow the policy, we're never going to get like there's like a whole branch.
Yeah, this, right?
Yeah.
Yeah. So the value function it's just a function that's well defined for every state. It's the policy that decides what is reachable versus not reachable. And so remember, we're just in the process of defining what the value function is for this choice of policy function. But you're right that the different choices of policy functions could have dramatically different effects. So for example, here, if the policy was instead go down, then the value of all of these things would basically would go to infinity, because this would ensure that there exists no mechanism given the current for an agent to actually move past this roadblock. And so you would need an infinite number of steps to get to the goal, which basically means the problem is not solvable. Okay. And so now we start getting to some of the relationships that are made use of in terms of coming up with interesting policies. And so the first equation that is relevant, and this forms the foundation of many, many algorithms in reinforcement learning, are the Bellman equations. And so value functions satisfy a recursive relationship. So let's derive that recursive relationship. Remember, the value function at state S is basically the expectation by following policy pi of the return gt conditional on being in state st at time t. You can write gt as the reward at time t plus the discounted future return. So gt plus 1 is the future return that I expect to see under policy pi that has now been discounted with gamma. What I'm going to do now is write down expectation over pi as the summation of pi of a given s. Remember, I have some policy function, and this is just the definition of the expectation. So I'm summing up over the different choices of actions that I could take under the current state s. So that's these 2 steps. Next, I'm going to write down RT as R of S8. Remember, this is the reward function. And I'm going to write down the future return as follows. The future return, what's going to happen to my agent in the future, is going to depend on which state this agent goes to in the future. So if the agent goes to state S prime, it has a probability of P of S prime given AS of doing so. And then conditional on being in state S prime, it's going to see this expectation of pi again of gt plus 1 given st plus 1 is equal to S prime as the future return. So this is just me expanding out the definition of what the future return is given that the current agent is in state S. So it's a convex combination of all the possible future returns that this agent could see under the different future states that this agent could go to. So I see some confused faces at this step, so I'm going to pause to see if folks have any questions. Yeah?
So in here, the policy is probability?
In here, so this is not the policy function, remember?
In the pi.
Yeah, so here we're working with a stochastic policy, which is why we're summing up over that probability. In the maze, it's a deterministic function. So this is the more general case for Bellman equations. So are people comfortable with how we got from gt plus 1 to this equation here? Yeah. Sure. So you have an agent, right? The agent is currently in state S. And the question you want to ask is, what is this agent's future return going to be? To answer this question, you need to first know, where does the agent go from state S to some S prime? You need to, so this agent is going to take this action A, and it's going to move to some state. How do you know which state it's going to move to? You don't yet. But what you do have is a probability distribution over future states that it could move to. So what you're going to do is you're going to say, so let's actually think of this as 3 different states that the agent could move to. S1, S2, S3. Each of those has some transition probability. Right? And given, and this is P of S1 given A comma S. Because I don't know which state my agent is going to move to in the future, I'm going to compute the future reward over each of those possible futures. So in this case, I'm going to compute the future gain, the future return that's going to come from being in S3. And then I'm going to multiply that with the probability of being in S3. So you should think of this as an expectation over future states that I could see given that I take action A and I'm currently in state S. That's how you get this expectation over future states. And for each future state, this is the formula that tells you what the future reward is, given that you are now in state S prime. Does that answer your question? So you don't actually know which state you'll end up in. That's why. Because this is before you do anything. And so what you'll notice here is that this is, again, just the definition now of the value function. So I'm going to substitute that here. And that's it. We now have a recurrence relationship between the value function at state S and the value function at state S prime. So this recurrence, is going into the future, but it's still a valid recurrence relationship. And so one way to view v pi is as a vector. So v pi of S is just looking at one entry of that vector for state S. But you can imagine, like in the maze, you have a finite number of states. So you can view this thing as a vector. And when you view it as a vector, you can think of this operator as the Bellman backup operator. And what this operator is going to do, so T pi of V of S is going to apply the Bellman equation to the current evaluation of the value function that you have. And so the Bellman equation can therefore be seen as this fixed point of the Bellman operator. So for those of you who just need a quick reminder of what operators on vectors actually do, let's pretend that we started with some v pi and we had 5 different states. So we'll assume that we have 2 actions, A1 and A2. T pi of v is going to be the operator that we apply to this entire vector, the Bellman backup operator. The act of applying the operator to the vector is going to give us a new vector. And one entry of that vector, so let's say the third entry, is going to be computed as this formula, where I've just taken the formula for the Bellman equation and applied it to the third entry, S3. And so that's what it means to take the Bellman backup operator and apply it to the value function vector. So you can visualize what this value function is in certain circumstances. So this is an example of what a value function would look like when you have continuous states rather than discrete ones. This is a game of golf, and the goal is to be able to get the golf ball into the hole. And so the hole itself has a value function of 0. And so if you're close to the hole, you have a value function of -1. If you're in the sand, you might have a value function of -infinity, depicting a very undesirable state, because you might not be able to get the ball out of the sand. And there's no way to go from the sand to the hole itself, at least in the context of this golf game. And so as we go further and further away from the hole, you can see the level sets of the value function now in this continuous space. Okay. So before we go into Q-learning, let's take a 3-minute break, and we'll restart at 2:10, and that's the point at which we'll talk about our first learning algorithm for planning. So we're going to continue. So a closely related, so we talked about the value function, and we talked about how it satisfied this recurrence relationship. But that's not exactly what we need in order to be able to do planning. So what we're going to do is define a related but different function called the state action value function, or the Q function. So much like the value function, the Q function is also going to be dependent on some choice of policy pi. But where the value function was a vector, where the elements of the vector corresponded to different states that your agent could be in, your Q function is a matrix. At least in the discrete case, you can think of it as a matrix. And so it's a matrix that has entries S, comma A. So it has cardinality S times cardinality A as its dimensions in the discrete case. But it's a function that takes states and actions, and it's defined as the expected future reward given that you're in state S and you are taking action A right now. So your agent is in state S, the agent has decided to take action A, what is the future reward? And as you can imagine, the two concepts are very related. So given Q pi, you could obtain the value function. Because if I knew what action I was taking in state S, then I could sum over the different choices of actions that I'm going to take in state S, multiply them by the probability of taking those actions given state S, and that's effectively the definition of the value function. So that you can think of this operation as being very similar to marginalization. And now, if you knew V pi, how would you obtain Q pi? So that's a little harder, because V pi tells you the value of a state, but Q pi tells you the inherent desirability of the state action pair. So to go from the value of a state to the desirability of the state action pair, you need to start from state S prime and ask, what are all the ways that I could get to S prime from A having taken action A in state S? So for each future state S prime, you would have to reason about how likely that state is, which is where the dynamics come in. You would have to multiply that by the value of that state S prime. And you would have to add to that the reward that you get right now from being in state S and taking action A. Because remember, the reward, so here, this Q function of SA is the future discounted reward of being in state S and taking action A. The future discounted reward is the current reward plus gamma, which is the discount factor, times the future reward. And the future reward is the states S prime that you could go into multiply the probability of going to each of them. So this is the relationship that tells you how these two functions are related. And so in general, it's not easy to recover q pi from v pi because it requires you to have closed form access to this transition probability matrix, which, as we mentioned, can often be intractable. But for now, we're going to focus just on this q matrix. And so we know that v pi satisfies this Bellman equation. And so the question is, does q pi as well? And it turns out that it does. And so you can write q pi as the current reward plus discounted future rewards. And remember, in the previous slide, we had this as v pi of s prime. And I've just expanded out v pi to write it as a function now of q pi. And that's how we obtain the recurrence relationship for the q function. And so you should think of this q pi as this matrix. This matrix is the thing that tells us we have gradient norm S, norm A, and q pi of S comma A is what is the reward if you're in state S and take action A. So any questions about what q pi is? Again, we're going to be following the policy pi, which is why there's a dependence on pi here. Okay. And with that, we're now ready to talk about how we can actually think about planning using this Q matrix. So remember, this Q matrix is all of the states times all of the actions that you could take in each of the states in dimensions. And suppose that you're in some state S. You get to pick one action A and then follow some fixed policy pi from that point on. What action do you pick? Well, the Q matrix tells you the reward associated with picking any action from any state. Because remember, this Q matrix, you can go look in the row of the Q matrix corresponding to state S, and you can ask which action do you pick from this point. And if each entry of this row tells you the future return from being in a state S and taking action A1, A2, A3, A4, then the right thing to do here is to pick the action that maximizes Q pi in that row. So you want to pick the argmax of Q pi SA over A. So that's the choice of action that you're going to take. So is this step, any questions about this step before we move on? Is that even like a sensible thing to do given the definition of Q pi? Because remember, Q pi is this matrix that tells us how good it is to take an action given the state that the agent is in. Because the definition, remember, is the future return that you get. So if you want to behave like an optimal agent, then it is a sensible thing to do to pick the action that is going to maximize the Q function for that state. And that's what this equation is telling you. Okay, so let's say if you have a deterministic policy pi that is optimal, then it must be the case that for any state S, Q pi of S is equal to argmax A Q pi of S comma A. What this is saying is that it's an extension of the first argument. And so the first argument says that I'm in some state S. The second argument says that if in some state S the optimal thing to do is to pick the argmax of QSA, then I can use that idea to come up with a policy function. And the policy function, remember, is a function that takes as input a state and prints out an action. So my policy function here is going to be for any state S, take a look at my Q matrix, figure out the column in the row of Q that is highest, and print that out as my action. That's going to be my policy. So any questions about just this idea in general? we haven't yet talked about how to get to this notion of an optimal Q matrix, but we'll get to that. So this is saying that if you trust your Q matrix to be optimal, then the right thing to do from the perspective of building a policy is pi of s equals argmax of A, Q pi of s comma A. And so we can now think about the process of going from an initial starting point for this Q matrix to a final starting point, to a convergent point for this Q matrix. So let's think about how to do that. So the Bellman equation for this optimal policy pi star. So let's call this pi star as our optimal policy, because if we trust the Q matrix, then this is how we would behave at optimality. What we're going to try and do is replace our original recurrence relationship, the Bellman equation for Q, with a new recurrence relationship, where we're going to remove the dependence on pi within this recurrence relationship. How are we going to do that? We're going to pick the policy function pi according to what the optimal policy would have done. So this is what we started out with as our relationship. And you'll notice this term at the very end here. What this term is saying is that you are in state S prime, and you're going to take some action A prime. What action should you take? You should take action A prime corresponding to pi star of S prime, where pi star is the optimal policy. And now, when you look at what this Q of pi star is at S prime and pi star of S, well, that's just the max over A prime of Q pi star of S prime and A prime. Because remember, applying this to this equation results in this function picking out the argmax, and then you plug in the argmax into your Q function, so you get out the max of the matrix Q at row S prime over all the possible actions that you could take. So I'm going to pause here to see if folks have any questions going from the first step to the second. So what did I do? I started out by saying, if I trusted my Q matrix, then I know what my optimal policy is. It's do the argmax of QSA. So I'm going to take that policy and I'm going to plug it in here in my recurrence relationship. When I plug in the optimal policy into my recurrence relationship, then I get something really interesting, which is the max of Q pi star S prime A prime shows up in my recurrence relationship. And this is neat because this gives me a new recurrence relationship altogether, because now I have Q pi star SA is equal to this recurrence relationship, which is different from the previous one that I had. And now Q star is equal to Q pi star is said to be the optimal state value function, and this is the optimal Bellman equation. And the key difference between the original Bellman equation for Q functions and the optimal Bellman equations for Q functions is that I've replaced this dependence on the policy function here. I no longer have a recurrence relationship that depends on pi star, because this only depends on what the max of the row of my matrix Q actually is. And so it turns out that this recurrence relationship is sufficient to characterize the optimal policy. We won't go into some of the mathematical details as to why. And in order to find Q star, we just need to solve this recurrence. And in the first two slides of this class, I already told you that there's a really simple algorithm to solve these recurrences, which is fixed point iteration. So what are we going to do? We've shown that some interesting problems could be reduced to finding fixed point of these Bellman backup operators. And so we can evaluate a fixed policy and iterate between evaluate and finding the optimal policy. And so the idea is to keep iterating this backup operator over and over again, where you evaluate T pi and T pi star. And so here, in this case, we're treating q pi or q pi star as a matrix or a vector with s times a entries. And if you actually look at how this algorithm is working, it's an instance of dynamic programming. And again, this is some of the foundational theoretical material in reinforcement learning that we're not going to dive into in this class. But a really cool exercise that you could do is take the maze example, and this is if you're interested in RL specifically, take the maze example and you can run this algorithm. What you should be able to see is that the algorithm is going to go back from the goal state and slowly start modifying the Q matrix such that the optimal policy is the max in each row for each state. And now you should ask, why on earth does this work? And it works for the exact same reason that we were able to find fixed points of the cosine function, because this represents a mapping F that is a contraction map. And so, as before, an operator F mapping from vectors to vectors is a contraction map if it satisfies this Lipschitz condition. And you can see here that if a function satisfies a Lipschitz condition and you iterate that function over and over again, which is to say you apply that function multiple times to that same point, then you can bound the norm of the difference between the repeated application of that function to any 2 points in your space as alpha to the k times the norm of the distance between those 2 points. And now alpha to the k for alpha less than 1 is going to exponentially decay down to 0. So you're going to get a contraction that is going to rapidly shrink the distance between the repeated evaluation of the functions at any 2 points in your space. And remember, in the case of in the case of value iteration, those 2 points are going to be these giant matrices Q. So what it's saying is that just repeatedly applying the optimal Bellman operator again and again to these matrices is going to converge to one solution, which is going to be the optimal Q star matrix. And that's what enables you to find the Q star matrix, and this algorithm is called value iteration. And so this is just writing out the update in full, but once you actually have that, it's very, very easy for you to find your policy, because you know what the optimal policy is once you have the optimal Q matrix. And so this is just the claim that value iteration itself is a contraction map. So there is a proof sketch that I've provided here. So it's completely optional. If you're interested in none of these equations is beyond you. Like, you should be able to follow the math from each of them. They're using very simple algebraic relationships. The only trick that I'll tell you that you need to know is how you move from here to here with an upper bound. And the argument is that this is a summation over a set of rows in the states of this Q matrix. And for each row, you're looking at the difference between the max between two actions. And what you're going to do is just take the global max over S prime A prime and move it outside so that you can get an upper bound here. That's really the only tricky step. The rest of it is mostly algebra. But what this gives you is a formal proof for why the optimal Bellman operator is a contraction map. And that's it in terms of value iteration. So you start at any random Q matrix, and then you repeatedly apply the Bellman, this Bellman operator to it until you converge to a fixed point of this Q matrix. And at that point, you're done, because you can write down pi star of S for any state S as the argmax of A for Q star S comma A. And that's how you get your optimal policy. So once you've found the fixed point, you effectively have found the solution to your planning problem. You know exactly how this agent should move in the maze. And so thus far, we focused on planning where we knew the dynamics, and the optimal Q function is characterized in terms of a Bellman fixed point update. But there are some limitations to this idea. So the first one is that it assumes known dynamics, and this also requires you to represent this Q as this massive matrix S times A. But at the end of the day, value iteration is still a foundational idea for a lot more practical algorithms. And so what we're going to do is think about what happens when we don't have the dynamics and we have to do some form of learning. What do we do in that instance? And so there's a few strategies. We talked about learning, we talked about how to do planning. And so in the context of learning, one idea is to do model-based reinforcement learning. And you have the technical tools to actually do this, but I'll tell you what the idea is in the most general form. Model-based RL is basically you take your game of Mario, for example, and you have examples of states, actions, and next states. So someone has played the game. So imagine you scrape all of YouTube for like Mario gameplay walkthroughs, and you get consecutive frames of states, actions, and next states. Then you build a machine learning model to predict the next state from the previous state and the previous action. So that model can be anything. It can be a giant neural network, it can be a linear function, a random forest, whatever you want. But then you use that model as a proxy for the true dynamics when you do planning. That's what model-based RL is actually doing. So you treat that model that you learn that as an approximation to the probability of the next state given the previous states. And you use that to teach a new agent how to behave optimally. So that's model-based RL. It kind of works, but there's important scenarios in which it breaks down in the context of RL. You can learn a value function. And so that's something that we're not going to cover, or you can learn a parametric policy function directly, which is where you take your state and you learn some function approximation that characterizes the policy distribution that the agent should learn. And that, in many ways, is how, for example, DeepMind tackled the problem of learning a policy over the Atari games. And so Q-learning, if we go back to the idea of Q-learning, we have the optimal Bellman equation over here. And the problem that we ran into is this expectation. So we needed to know how to modify the dynamics to evaluate this particular expectation, because we didn't have access to this probability distribution over next states given previous states. So the trick that we're going to use is a trick from statistics, and it's called Monte Carlo estimation for, in this particular case, streaming estimation of the expectation of a random variable. So how many of you have heard the word Monte Carlo estimation before? Just about a few people. So generally, Monte Carlo estimation is a broad category of terms that people use to define estimators of equations or expectations of random variables. And so in this particular case, if you want to define an expectation, a Monte Carlo estimate of the mean of a random variable is to take a bunch of data points that you do observe and average them. So that's the Monte Carlo estimator for the mean. Now, what happens when your samples are not available all at once? Rather, you're seeing one sample, then another sample, then a third sample, and so on and so forth. And someone asked you, how would you calculate the mean of this particular random variable now when you get streaming samples? So it turns out there exists a Monte Carlo estimator for that as well, and that's basically this equation here. So what this equation is saying is you start with some value of mu, you set it to be 0, and then each time you get a sample x from your stream of samples, you update the mean. You update it as mu plus alpha times x minus mu. And it turns out you can show that this converges towards the expectation over x. I think when I was a student, I got this when I was interviewing for an internship as a question, so it's a good trick to know about as well. But it enables you to capture random statistics of variables that you're getting in a streaming fashion. But once you have this trick, it's really useful, because what it means is that instead of evaluating this expectation directly, you can use this trick to evaluate the expectation in a streaming fashion. Because what you're going to do is write down the update as the old Q of SA plus alpha times this difference between the reward and gamma times the max. So this is what the update would have been marginalized out over all the different possible states S prime that you could take. And this is the state that you actually ended up in. So you would write down the application of the Monte Carlo estimation towards the Bellman equation, and this would enable you to free up the recurrence from its dependence on the dynamics. And so how would this actually work? So every iteration of value iteration needs you to update Q, but there could be lots and lots of states. So for example, in Mario, the states might be very, very large, the state space. And you only observe transitions for states that are visited, which is to say you only know how you get to a new state based on the previous state that you were in. And so the idea when training an agent in the context of this approach called Q learning is to have the agent interact with the environment. And so the idea that an agent can interact with the environment is one of the fundamental ways by which RL differs from supervised learning, either through the form of knowing the dynamics closed form or through one-off interactions. But we're going to have the agent interact with the environment and only update Q for the states that are actually visited. But if we do this, we might never visit certain states simply because they don't look promising, and we'll never learn about them. So what do we end up doing in this case? So the idea is to have an agent that takes random policies, and this idea has a name, and it's called epsilon greedy. So the epsilon greedy algorithm is very simple. So you're going to randomly initialize Q of SA, so your Q matrix. You're going to start in some state, and then for time step t is equal to 0, 1, all the way up until you've satisfactorily learned a Q matrix, you're going to choose the action according to the epsilon greedy policy, which is going to flip a coin, a biased coin that has probability of heads being epsilon. And if the coin turns up heads, then you're going to sample a random action among all the actions you could take. And if the coin turns up tails, you're going to pick the greedy action, which is to pick the argmax of A in A over Q of ST comma A. So depending on the current state that you're in, you look at the row of the Q matrix and just pick the action that maximizes that row. You're going to take this action in the environment. And remember, you get to interact with the environment at this time. So if you were actually coding this up, you would give this action as input to your emulator for Mario. And given this action, you would get back a new state and potentially a reward function as well. So your emulator would give you a new state that Mario is in. So that's what this operation is going to correspond to. And it would give you the reward for having taken that action. And you would use those pieces of information to update your Q matrix. So I'll pause here to see if folks have any questions about this idea, but it's just a very different way of doing learning. So in the previous algorithm that we talked about, value iteration, we didn't have any learning. We pretended that we knew the dynamics exactly, so we could write down the optimal Bellman backup operator. We took some random Q matrix, we applied that operator until the Q matrix stopped changing, and then we could read out the policy function because it was just argmax of Q star of S comma A. In learning, we have to actually interact with the environment because we don't know the dynamics. So we're going to do a method of learning that is basically trial and error. So we're going to try some actions with probability epsilon. Sometimes they'll be wrong, sometimes they'll be right. But regardless of what they do, we're going to update the Q matrix at each interaction. So it's kind of the analog of doing modifying, of doing coordinate descent in these entries of the Q matrix. And at each point in time, we will update the entries of the Q matrix that we end up visiting. And this epsilon greedy policy is going to make sure that we end up visiting all of the different states that we could possibly have in the context of Mario. Yeah?
We just want to gather as much information as possible about different states. Why would we ever want epsilon to be anything other than 1? Why not always just the random choices?
Well, if you always take, so that's a great question. So why not always just act randomly? Think about the trade-off between acting randomly versus acting opportunistically. So you know that the argmax of Q is going to give you your current best action given all the information based on previous interactions that you have so far. The reason you want to do that often actually is so that you make progress. Because if you have, like, think about the idea of just Mario jumping randomly up and down in one space. You can do that for a long time, but then you need billions of interactions in order to learn a good policy. The idea is that you should mostly be doing the thing that you believe it to be currently optimal, which is represented by this argmax. And every now and then you should take a random action, because sometimes if you don't do that, you will not explore new states that you've never been in. So imagine, your Mario character standing on one of those tubes. And the only thing in those tubes is those coins. It's not really relevant for progression to the end of the game, but unless you took a random action at that state, you might never explore that entirely new area of the map altogether in this game. And so that's why there's this trade-off. And this is a fundamental trade-off between a lot of reinforcement learning algorithms, and it's called the exploration-exploitation trade-off. So the epsilon greedy policy ensures that most of the time the agent exploits its incomplete knowledge of the world, but every now and then it explores other actions that provide utility to learning about the world itself. And so without exploration, the agent may never find some good actions, and it's one of the simplest but most widely used methods for trading off exploration and exploitation. And it's a really important topic of research because we at best are resorting to heuristics on how to trade these things off. And so humans use this idea all the time as well. So let's say you're going out to dinner with friends, you may want to go to the same restaurant that you know has reliably good food that everyone likes, or you may want to try something new. And so you have some internal heuristic for policy on how you choose to explore versus exploit what you know to be good. The same things happens in the context of online banner advertisements and oil drilling, whether you drill at the same location or try and branch out to find new locations. Exploration is a very useful thing for an agent because it tells the agent that there could be much, much higher rewards that it did not know existed, and the only way to get there is by trying some random actions. Yeah?
Once you train the model fully, do you get rid of the exploration? Or would you keep it?
Once you train the model fully, you don't need to explore anymore. If you've actually gotten a model that you like, then just run the optimal policy on the Q matrix and you're good. So that's how you do learning in the context of a scenario where you don't actually have access to the underlying dynamics. And so I'll skip this particular slide, but leave it in again. And so the only thing I want to say here is that in this particular case, we were free to choose an exploration-exploitation policy. And algorithms for learning and reinforcement learning that enable us to follow whatever policy we want are called off-policy algorithms. And this is just a name. And so if you were to read research papers, you would find names like off-policy versus on-policy. Off-policy basically means it doesn't matter what you choose in terms of how you trade off exploration exploitation, you still have guarantees on the convergence of your algorithm, as long as certain conditions are met for your policy. In on-policy learning, you have a policy function that you keep track of, and you are modifying the policy function as your agent goes along and is interacting with those environments. And those kinds of algorithms are much, much more complex because you need to carefully control for lots of biases when you do parameter estimation for on-policy learning. And so the last thing that I think is important to talk about is function approximation. Actually, let's just a show of hands in terms of questions about Q learning. Yeah. If the best action is in nature.
So for example, if we're playing rock, paper, scissors,
Yeah.
then the best policy is that we play rock, paper, scissors with much sort of percentage chance. But in the algorithm we're describing here, we will only learn a policy that plays each move at 100%
So you're saying, well, the Q matrix has, in the case of rock, paper, scissors, is, let's say there's some other states that you observe, but let's say you're in state S while playing rock, paper, scissors, and this is rock, this is paper, this is scissors. You would learn numbers in this particular case that they were all equal. And then argmax, you're right that argmax would often end up just picking, in cases where like the probability of the optimal action is actually equal, it would go down to how the implementation of argmax was in whatever system you're implementing this in. So if you wanted more randomness than that, you might actually have to look for it and say, if everything is the same, then have a randomized strategy that looks at uniform. Yeah, so what you've highlighted is definitely an edge case for at least the naive implementation of policy evaluation, and in practice, people use heuristics to catch these edge cases. Any other questions? Okay. So far, we've assumed this tabular representation of Q, where we have one entry for every state action pair. And so this idea is kind of impractical, except for the simplest set of problems, where you have discrete set of states and discrete set of actions. And so what people often end up doing is actually not working with the direct matrix, but rather working with parameterized functions of states and actions. So you can express Q of SA as some W transpose of a feature function, which so you could take a neural network, for example, input the state and input the actions that input the action that you're currently taking into the neural network, and you could compute Q with a neural net. And once you did that, you can update Q. So now the update rule has to change because now you have a parametric function associated with your Q rather than just a matrix. So you can't just do the matrix updates. You have to learn how to update the Q function, and these equations, which we're not going to derive, are what end up resulting in those updates. And so this is not a new idea. It's pretty much a decades-old idea, but DeepMind got it to work really well on Atari games in 2013. And at that point, they used a really small network by today's standards. So the main technical innovation they used was to store experience into a replay buffer and perform Q learning using stored experience. And so that enabled them. So the idea is basically, as you play the game, you store past iterations of how you played into an external data set. And as you're continuing to interact with the environment, you also fine-tune your model based on that past experience buffer. And that enables a model to learn the right policy function much, much faster because it doesn't have to do trial and error over all possible combinations of things. And so there's some clever tricks that enabled it to get it to work correctly. And I believe there was one of the projects in this class trying something similar for the game of Mario. So it's a really interesting question to think about as well. The other idea that a lot of advances have recently made use of is this notion of compressing the state, which is to say, take the state and instead of writing down positional encodings for here's where Mario is in X, Y coordinates, put the entire image into a neural network and let the neural network figure out what the right representation for planning actually is. So rather than having, so if we were playing air hockey, we know that a good notion of a state is X, Y, and velocity. So instead of actually putting that in, we would just put in a picture of the air hockey table into the neural network, and maybe a picture superimposed with the picture taken like one frame before, and these two pictures together, and have the neural network figure out what the position, velocity, and location of this puck actually is on the table. So this idea of function approximation has seen a lot of use in the current systems. And in fact, they're used a lot in the context of AlphaFold or AlphaGo or any of these modern systems for reinforcement learning. And so there's some videos that I've added in here that you should check out in your own time to see how these different approaches work. But all of these discussed approaches estimate the value function via the Q matrix. And so they're called value-based methods. As I mentioned before, what we don't cover are methods that directly optimize the policy, which are policy search methods. So remember, in value-based methods, you come up with this Q matrix, you find the right Q matrix, you get the value function from that, and that gives you the optimal policy. In policy search methods, instead of pulling out the policy from the value function or the Q function, you directly parameterize the policy. You say that I'm going to learn some function, some f of x, where x is now the tuple of state and action. And that is going to tell you how the agent should behave in the next time step. And so those are much more complex styles of learning in RL, but they're very, very popular as well. And of course, there's like mixes and matches between them. So if reinforcement learning is something that you're really, really interested in knowing and learning more about, there's lots of resources available, including several really nice video lectures by David Silver, and as well as CIFAR and Vector Institute's RL Summer School. So you should definitely check that out if this is a topic that you're really excited about or you're curious to learn more. It's also, I should say, a very rich area of theoretical study. So people have worked a lot on improving learning algorithms for partially observed Markov decision processes. So in this class, we talked about MDP, so Markov decision processes. You can think of partially observed Markov decision processes as a generalization of this idea to the case where you might have wind, like you're playing ice hockey, but now you have an unobserved variable called wind that is affecting how the puck moves on this table. In those cases, you don't observe the wind speed necessarily, but it does have an impact into how an optimal policy should behave. So those classes of models and methods are designed to characterize these latent sources of noise that might influence your policy function. And so just as a few closing thoughts, overall, that brings us to the end of the semester, and most of this class covers supervised learning. The second half covered unsupervised learning with just a bit of taste of reinforcement learning thrown in. And the reality is this is sort of the base amount of information content you need to know to decide what you should do in terms of future classes. And so in CSC 4 and 3, you'll spend a lot of time thinking about some of the ideas that lead to the big neural networks that are in use in practice today. And so a lot of time is going to be likely spent thinking about attention mechanisms and transformers. In this class, you derive these update rules by hand, and backprop is a very mechanical operation. But in 4 and 3, you learn how an autodiff package can be implemented. So what is a really simple way to program an autodiff package? It's the backbone of it is not very complex to understand, but understanding it is useful for you to know how existing tools such as PyTorch, JAX behave. And so here we focused on scalar valued outputs like class identity, regression, and in 413 you'll start experimenting with much more rich outputs. So things like text, or how do you create models that generate images correctly? And this used to be known as structured prediction, but now it's pretty routine, so we don't need like a special name for it because we use the same underlying structures like neural networks in order to be able to solve these problems. And here we talked about neural nets as learning feature maps. And generally, we kind of want them to learn some representation of data so that mathematical operations on those representations have semantic utility. And so there's this really nice paper that I encourage you to read called Efficient Representations of Words in Vector Spaces that talks about how prediction as a task is an interesting construct in order for you to find representations that have interesting semantic properties. So here what they did is they calculated, so they trained a neural network to just predict the neighboring words given the context of it. And then they took the representation for every word and did PCA to project it down to 2 dimensions. And what they found was that even this simple projection had interesting relationships between countries and their capitals. And again, this is not something that the model was told to learn, but it suggests the idea that prediction as a task has utility as a loss function for compressing information in a way such that human interpretable semantic content can then be recovered via tools like PCA from the learned representations. And that's a bit of a mouthful, but it's basically saying that just by doing prediction, these neural networks learned relationships that humans also make use of in their day-to-day lives. And I think this idea is sort of what's led to the continued use of neural networks in a variety of different places. But in the cases of those words, it enables us to do these algebraic operations. So you could take the vector representation of Paris and subtract the vector representation of France. And you'll see that it's approximately equal to the vector representation of London minus England. So it preserved the semantic content in some high-dimensional vector space of the relationships between cities and the capitals that they were countries of. And so another big goal in neural network is to learn these disentangled representations. So how do you come up with ways to teach your neural networks not to learn redundant features? Because right now we don't have a lot of control about what the neural networks learn. We sort of just throw data at it and hope that it learns something useful. But there's a big push to think about how we can further learn disentangled representations. And once we do that, you can start putting them in systems that do things like image-to-image translation or image-to-text translation in a pretty straightforward way. So if you enjoyed much more of the mathematical content in this class, I think CSE 412 is a really interesting class to take, because what that class will teach you are the foundations of probabilistic graphical modeling. And so in probabilistic graphical modeling, what you learn how to do is to build systems that capture latent sources of variation in data. So we talked about the simplest kind of system, which is PCA, but really that's a linear projection. In probabilistic graphical models in 412, you learn about how to build nonlinear latent variable models. So things that can automatically take text documents and pull out topics from them, or even take images and complex high-dimensional data and use neural networks to blend neural networks with Bayesian networks. And so if you've heard the term VAE before, that is a latent variable model that uses both neural networks as well as probabilistic graphical models. And so that's something you'll learn about in the context of CSE 412. And here we sort of derive the rules for inference in a pretty straightforward way. Everything was either observed or linear, which meant that Bayes' rule was very straightforward to apply, or at least we were able to do it with a bit of mathematical calculations. But there's many nonlinear models where Bayes' rule is intractable to apply, which is to say that there exists no closed form solution for it. And in those cases, you need to use iterative methods like Markov chain Monte Carlo, or approximation methods like variational inference in order for you to even learn the model parameters. And so that's another thing that you learn in CSE 412. And so it enables you to build much, much more complex unsupervised learning algorithms that do really cool and interesting things like model hierarchies or dynamical systems or topic models, and combine these in complex ways. And so with that, I think that mostly brings us to the end of this class. If you are interested in some of the research side of topics you've heard about, do check out some of these conferences actually NeurIPS is happening next week in New Orleans, and so that's where a lot of the most recent research in machine learning is created, presented, and so there's lots of visualization tools that you can use in order to visualize the papers that are being presented at NeurIPS and the topics that they span. So if you're interested, send me an email and I'll send over that information. But thank you everyone for a wonderful semester, and good luck. So I'll try to have at least, if you're interested, I'll get you all access to some of the final practice exams, and I'll have at least one more office hour next week for those who want to ask me questions.